Assalamualaikum warahmatullahi wabarakatuh and good afternoon everyone. So today we are going to continue on chapter 3.5 to chapter 3.6 on the material balances on multiple unit processes. So last week we have already discussed about this topic. We have also practiced on some example. So today we are going to um, study on another example. So it's about sugar refinery. So let's take a break by yourself for around 1 minute to read and understand the question. You can stop the video for some times and read it, and then we can continue. Okay, I'm assuming you have stopped and take your time to read. So let's read together. So here we have a problem about the sugar refinery. A simplified flow sheet for the manufacture of sugar is shown. So after this slide, there will be a slide showing a flow sheet. Sugarcane is fed to a mill where a syrup is squeezed out and the resulting bagasse D contains 80% weight percent pulp and the remaining water and sugar. The syrup E containing 13 weight percent sugar, 14 weight percent pulp and finely divided pieces of pulp is fed to a screen which removes all the pulp and a small amount of sugar to produce a clear syrup containing 15 weight percent sugar. The evaporator makes a heavy syrup K containing 40 weight percent sugar, and the crystallizer produces 1000 kilogram per hour of pure sugar crystals. Note, in average, sugarcane contains 16 weight percent sugar, 25 weight percent water, and the rest is pulp. So when you read the question, what you have to identify is you need to know how many units are there. You need to know how many materials are there, the composition, and how many streams are there. Okay. Find out also which one will be our basis. Remember back, our basis must be in a form of amount of flow rate, never the composition. Okay, and then we see the question, what are they asking? First, perform the degree of freedom analysis of the system and the process unit. Find the water removed in the evaporator in kilogram per hour. Find the mass fraction of the components in the waste stream G. And find the rate of feed of sugarcane to the unit in kilogram per hour, and also what percentage of sugar in feed is lost with the bagasse. Is this an efficient operation? Explain why or why not. Okay, let's see. So here we have the flow chart and we compare with the question. So this is the flow sheet, the flow chart for the manufacturing of sugar. So sugarcane is fed to a mill. So here we have the first unit, which is a mill. So we have a sugarcane here. So the sugarcane consists of sugar, 16 weight percent, water, 25 weight percent, and 59 weight percent pulp. This one was given as a note just now. So we have three material, okay, but we don't know the flow rate of the sugarcane. So it has been fed to this mill where a syrup is squeezed out. So we are expecting there should be two outlet, two output. The first is E, the thing, okay, and the resulting bagasse contains 18% of pulp and the remaining water and sugar. So here is what was being squeezed, and this is what the rest lah. The rest will be the bagasse, which is labeled as D, kilogram per hour as the flow rate, and it consists of 80 weight percent pulp. And we have 20 weight percent more, which contain both water and sugar. So we don't know how much is each. Then we have the another one. We squeeze out. So we have, what do we have here? We have E, which is the syrup, containing 13 weight percent sugar, 14 weight percent pulp, and finely divided pieces of pulp is fed to a screen which remove all the pulp. So this one, after they squeeze it, so they remove it to another unit, which is screen. So we have 13% sugar, we have 14% pulp. What will be the rest? The rest will be another material. Here we have sugar, water, pulp, so the rest will be water. Then this E kilogram per hour was fed into a screen because we will divide the pulp to a screen which remove all the pulp. So the pulp is removed. And a small amount of sugar to produce a clear syrup. So here we have syrup. H here is the syrup, here is the pulp in kilogram per hour. G is the pulp. H is the syrup. So this syrup, it will be a liquid lah. Syrup containing 15% sugar. What are the rest? The rest should be water. The evaporator makes a heavy syrup K. So what we have here, we have H. We put it into an evaporator. It's a syrup, it's a liquid. We put it into evaporator means we are evaporating something. We are removing something. What are we removing? We are removing water here. J kilogram per hour water. So when we remove water, what we have a concentrated syrup. K kilogram per hour. This is a concentrated syrup. At first, we have 15% sugar. The rest is water. Now we have thickened syrup. So we have 14% sugar and the rest will be water. Then it is put into a crystallizer. So we put into a crystallizer and producing 1000 kilogram per hour sugar. Now we have an amount which is 1000 kilogram per hour. Before this, we don't have any amount. We only have a composition. So here we have the sugar. And then this is our liquid, which is water, which means here we have syrup. The syrup is separated into a crystal of sugar and the rest will be water. So they are separated purely lah. So this is pure sugar crystal. This is water here, liter kilogram per hour. Okay. So now the first task is to find degree of freedom. So degree of freedom, we have to do degree of freedom for all the unit here and also for overall. So here, if we do overall, if we draw, oops, let me put my picture here. Okay, so here, if we consider overall, then how many output we have, how many input we have. So here we have input, then we have here 1 output, 2 output, 3 output, 4 output, 5 output. Okay, so we have 7 unknown. F, D, G, J, L. That is 1, 2, 3, 4, 5. And then we have also our X, X1 and X2. So this X will be here. Because the others, this one is pure, this one is pure, this one is pure. So we don't have the X value. Okay, and then, so the DOF, when we calculate, DOF is number of unknown minus the number of equation. So here we have 3 components, S, which is sugar, water, and pulp. Therefore, we have 3 independent mass balance. So when we deduct, we have DOF is equals to 4. So we cannot solve the problem starting using overall system. Now we try the meal. We try the first unit, which is meal. So how many unknown we have? So only for the meal, so we have 1 input and then we have 2 output. Our unknown is F, D, and E. And also here we have X, which we don't know what is the amount. And then we have 3 independent mass balance because we have 3 material. So 4 minus 3 equals to 1. We cannot solve using meal. Let's see screen. The second unit, screen. So we have 1 input, 2 output. Our unknown here is E, G, and H, and also X2. So we don't know about X2. And then 3 independent mass balance. So again, DOF is equals to 1, cannot start from here. Then we have evaporator, the third unit. So here we have H, J, and K as unknown. and we have two independent mass balance. Why only two? Because this time we only have water and sugar. These are only our two materials. Our pulp already separated here. This is pulp plus water or sugar. So here, starting from here, it's only syrup. All are in liquid form. So when all are in liquid form, we have only two materials, sugar and water. The sugar is already diluted in the water lah. So cannot solve in evaporator. We move on to the crystallizer. So now crystallizer. So for the crystallizer, we have one input, we have two output. So what are our unknown? We have K here and L are our unknown. M is 1000 kilograms, so it can be our basis actually. So we have only two unknown, which are the flow rate. How many independent balance? This time we only have two things, two materials, which are sugar and water. Therefore, DOF is equals to 0. Thus, we can start solving from the crystallizer. Okay, so we start with mass balance around this crystallizer. When we do sugar balance, okay, for sugar balance, how much sugar are there? So here we have 1000 pure sugar. So 1000 times 1. This is 1000 times 1 equals to 0.4 K. Why there's only 1 and 1? Because here we have pure water. So input is equals to output. This is our output here, 1000 times 1. Our input here is 0.4, which is 48% sugar, times K, which we don't know. So, but we can solve this problem. We can find K. K is 2500 kilogram per hour. Then we try to do the total balance. So our input is K. Our output is M plus L. So M is 1000. L we don't know. K just now we solved 2500. So we can solve for L, which is 1500. So now we have solved L, we have solved K. Then we go down. Because remember just now evaporator, the DOF is equals to 1. Because we have solved for K, now DOF becomes 0. So we can start with the balance. We do the sugar balance. So this time our input is 0.15 sugar times H. So here is our input. Then we have two output. But the one that have sugar is only the top one, which is K times 0.4. K times 0.4. K we know already 2500. So we can solve for H. We got H is equals to 6667. So we solve for H. Then we do total balance. H is equals to K plus J. With that, we can solve J. We know H, we know K. We got J is equals to 4167. Okay, that way we actually answered the second question, which is how much the water is removed from the evaporator. So that's 4167 kilogram per hour water. Then mass balance around the screen. So here we have the screen. So we go back lah. Evaporator we solve. Screen DOF was also 1. But now we have solved H. So we are supposed to be able to solve screen. So now we do the water balance instead. So we do the water balance. Here we have 0.73, which is the rest of the component, which is water, times E. So here is our input. Output we have 2 from G and from H. But from H only, we have 0.85 times H because we are referring to water. So we have one input, one output. We solve for E, we get 7763. Then we do the total balance. E is equals to G plus H. We solve for G. G is 1096. So from there, for the part balance, when we do the part balance here, it's 0.14 here times E. So this is our input is equals to our output here. X2 here times G. So from there, we can solve X2 is equals to 0.992 kilogram per kilogram. And the rest will be sugar. Water is here only. So here we solve for pulp and we also solve for sugar. Then C, question is the mass fraction of the component in the waste stream, G. Here is G. We solve it, which is 0.992 kilogram pulp per kilogram and 0.008 kilogram sugar per kilogram. We have solved C actually. Then we go to meal, the last unit. So we have meal. We do the part balance. Input is equals to output. So for input, we have 0.59 part times F equals to 0.8 times D plus 0.14 times E. So here, we know already that E is equals to 7,763 from here. Then we do the total balance. F is equals to D plus E. E also we know, so we are left with 2 equation and 2 unknown. With that, we solve simultaneously. Then we can get D is equals to 16,000, F is equals to 24,000. Okay. Additionally, we can solve for sugar balance. Here we have for sugar 0.16 F, the input to meal is equals to X1D, the output, plus 0.13 E, another output. We solve for sugar, we got X1 is equals to 0.174. Then D, the rate of feed of cane to the unit. We have solved just now, which is F is equals to 24,398 kilogram per hour. Next question, the percentage of sugarcane in feed is lost with the bagasse. We have just now here. Here is the bagasse. So now how much is the sugar lost? Okay, how much is the sugar lost? When we calculate just now, sugar, how much is it there? It's 0.174 times D. We already saw for D over 0.16 times F. This is our input. This is our output. So how much sugar is in this bagasse? Times 100%. When we solve this, we got 74.7%, which means in the bagasse stream, there are 74.7% of sugar from the feed as compared to the feed. So this is how much sugar lost. We throw it away. The bagasse, we throw it away. That's why, is this an efficient operation? No, it is not. Because instead of recovering the sugar for us to use it, we have lost it and throw it away as a bagasse, as a waste. So it's not efficient. Okay, so this is all the example about the sugar refinery. We have another example, but you can do this at home and try to solve the question. All right, okay. So till that, thank you very much. We'll see in the next lesson.